Lesson 70. So these logarithm things that we just saw for the first time in the last lesson, lesson 69, logarithms, they have some interesting properties. Properties of logarithms. It's kind of like, you've heard of laws of exponents before, right? Well, this is almost like laws of logarithms. So the first thing, the first property, I got 5 of them today, the first big property is actually repeating something that we said last time. Remember when we were graphing logarithms, which they tended to look like this, we showed that, hey, they're inverses of exponentials, which if you graph like e to the x, it tends to look like this one on top. If you graph natural log of x, it tends to look like this one on the bottom. They're reflections across the 45-degree line. That's how you can tell they're inverses. Anyway, they're inverses. Exponentials and logarithms are inverses. And so when you look at this, what you've got here is you've got a logarithm with a base of 2, right? And what's this? This would be an exponential with a base of 2. Log base 2, and this will be an exponential function with a base of 2. Now, they're inverses of each other. Now, the fundamental property of inverses, what we're talking about here, says that when you plug x into the function and then take the result and plug it into the inverse function, you get back your x, right? Remember this idea? Or if you were to plug the value of x into the inverse function and then plug that into the function, you would get x. It's supposed to work both ways, remember? Well, isn't that kind of what I'm doing here? That's what I'm doing. Well, it's not an x, it's a 3. But I'm taking this 3 and I'm plugging it into the exponential of the base of 2. But then I'm plugging that into a logarithm of a base of 2. It's going to cancel. So the end result is, if I can erase all this stuff, the end result is you just get 3. So that's the first way I wanted to explain it. I wanted to explain it in terms of fundamental property of inverses. Again, the log base 2 is the inverse function of an exponential function with a base of 2, and so they in effect cancel each other. So whatever you put in this case 3, is what you'll get out at the end, 3. Okay, so here's another way I could prove it to you though. Let's just do this directly. 2 to the 3 power, what is that? You'd have to go 2 times 2 times 2 is, well, it's 8. Okay, cool. Now, next question. Remember how you evaluate logarithms. You go 2 to what power gives me 8? And it's 2 to the 3 power gives you 8, right? So yeah, you get 3. 3 goes in, 3 goes out. Fundamental property of inverses. Same thing here. Now here you got to be careful. This is a log with a base of 3, but then this is an exponential function with the base of 3. We're plugging 2 in to an exponential function with the base of 3. And so if 2 goes in, 2 comes out. Boom! That's what you know. And if you want me to prove it again, ask yourself, what is 3 squared? 3 squared is 9. Okay, so what is the log base 3 of 9? You'd have to say 3 to what power equals 9, or you'd have to ask that. And the answer is 2! Exclamation point. So instead of doing all this swooshy moving and all this other stuff, all you got to do is say, look, if the log base and the exponential base match, bypass the whole thing. They cancel each other in some sense. 2 goes in, 2 comes out. That's all there is to it with these things. I just love that. I just love that. So let's just do this one the easy way. What do you say? Note x is being plugged into an exponential base 10, which is in turn being plugged into a log, and remember, if there's no number there, then the default is a 10. And so, yeah, they're inverse functions. Boom, x goes in, x comes out. Boom, da boom, boom, boom. Here, I got an exponential function with a base of e. Well, natural log is a log with a base of e. The bases match, they cancel. And so, in this case, you don't get x, you get 2x minus 1. You know, this is what we're plugging in, so this is what we're getting out. Go back to full scale. Well, yeah, okay. Cool. So that's actually going to be something we use quite a bit in the next lesson, 71. In the next lesson, we're going to be solving all kinds of equations again, equations that have exponentials in them, equations that have logarithms in them. And this is going to be a handy dandy little property, the fundamental property of inverses. It's one of the big ones to know. If you're playing with exponentials and logarithms, you want to keep this in mind. They're inverses. They will cancel each other, so to speak. Okay, so I got that one first because it's one of the most important properties. I want to do this one second. It's also an important property. I call it COBA. That's what I call it. But it stands for change of base algorithm, which is more of its official name. The change of base algorithm. How does this work? Well, in the old days, how would you evaluate something like that? See, nowadays, I'm sure your calculator has a button that looks like this. That's what your button looks like. And so when you push this button, it's going to ask you to, it's going to give you a, well, it's going to basically say log, and it's going to give you two boxes, and you're going to want to put the 4 into that box, and you want to put the 7 into that box, and you want to get your answer. I might as well do that because I'm curious. So I've got one of those there buttons. So I'm going to put the, what am I putting? I'm putting the 4 there. Yep. Nope. That's where the 7 goes. I'm putting the 7 there. Okay, come on over here. Come on. And then put the 4 there. So log base 7 of a 4. Yep. So my calculator calculates this directly and gives me a 0.7124-ish or so. Okay, so these days you can do that. There's a button that'll do that for you. In the old days, think back to like slide rule days, or even when the early calculators came out, they didn't have a button like that, but they did have natural log buttons on the calculators. On your calculator, you'll have a natural log button. It'll be probably a capital LN, which means natural log. But you have natural logs. So how do you get this from a natural log? What you do is, you see that 4 and you see that 7? You take the natural log of the 4 and you take the natural log of the 7. And you arrange them just like that. The natural log of 4 gets divided by the natural log of 7. It's the coolest thing in the world. I mean, look at that. Who'd have thunk it, right? But I'm going to prove it to you right now. I'm going to take the natural log of 4 on my calculator, and my natural log of 4 comes out to like 1.38629 or something. It's good to carry a few decimal places. And then the natural log of 7, I'm going to get that on my calculator, and it says it's about 1.94, like 591 or something. So anyway, if I just take those, what I've typed there, if I just take the 1.38629 and I divide it by the 1.94, what's that say, 591, I'm getting, oh, you're not going to believe this. That comes out to 0.7124. It's a match. It works. It works like a charm. So it's cute. It's an interesting thing to know about, right? So we had instant replay. We had, we had a 4 here and a 7 here. We were taking the log base 7 of a 4. So the way we did that is we put the, notice the 4's on top and the 7's on the bottom. The 4's on top and the 7's on the bottom. That helps me somehow to get it right. So the 4's on top, the 7's on the bottom. But what I'm doing is I'm taking the natural log of 4 on top, and I'm taking the natural log of 7 on the bottom. Making messes over here. Clean up the mess. Okay, so anyway, it's all you guys do, and it works. P.S. New color. P.S. It works if you use the log, which is a log base 10, right? So your button on the calculator will just be a capital LOG, but what it means is a log base 10. In other words, I could take the log base 10 of 4 and divide it by the log base 10 of 7. You get completely different numbers, of course. What is the log base 10 of 4? I'm getting like 0.60206. Right? Completely different from what we had up here. Now take the log base 10 of 7. I'm getting a 0.84510. But now you take that 0.60206 and you divide it by that 0.84510 and you get, you ready for this? 0.7124. It's the same. It's all the same. It's all the same. This is what we mean by the change of base algorithm, or what I call mighty Koba. So again, the 4 was on the top, the 7 was on the bottom. The 4 was on the top, the 7 was on the bottom. The 4 was on the top, the 7 was on the bottom. That's what's constant in all these things. What changes in all these things is, here I was using a natural log of 4 over a natural log of 7. Here I was using a common log base 10, common log of 4 over a common log of 7. It gave me the same answer. Here this is the log base 7 of 4, right? And I could add here, you could use any kind of log. Not that you'd want to, but you could use the log base 79 of 4 and divide that by the log base 79 of 7. Not that I have a log base 79 button anywhere, but you could do it. It doesn't matter. That's the beauty of this change of base algorithm. You can change logarithms into any other base you want just by following this routine. It's a good thing. Now let's put it to some kind of use, okay? So in the old days, we used to have to, we needed this just to figure out things like what's the log base 7 of 4, because we didn't have these special buttons on our calculators. We weren't spoiled. No, I'm just kidding. So anyway, but we're still going to need it, even though we don't need to use our slide rules anymore. We're still going to need this algorithm to do things like, well, solve equations like in the next lesson. So like we might have a log base 8 of x, and for reasons you'll see later, we might need to convert it to a logarithm with a base of 2. And the good news is we can do that. So what does that look like? Well, look back over here. You take the same kind of log, top and bottom. That's the key. That's the key. So I want to have a log base 2. So what I'll do is I'll take a log base 2 over a log base 2. And the x here will go on the top, and the 8 here will go on the bottom, right? So notice you always have that part's the same, right? The x is on the top, the 8's on the bottom. The x is on the top, the 8's on the bottom. I wanted a base 2, so that's why I'm using log base 2's in these spots. Okay, so let's get this stuff out of the way. Okay, so what is that? Well, see, the thing is we can go a little bit further, because the log base 2 of 8 is something we can figure out. In this case, we can figure out in our heads, 2 to what power is going to give me an 8? 2 to the 3 power is going to give me an 8. So what I've got here is I've got the log base 2 of x divided by 3, or if you prefer, 1/3 of the log base 2 of x. To divide by 3 is to multiply by 1/3. So who'd have thunk it? The log base 8 of x is actually 1/3 of the log base 2 of x. It's a simple multiplier of 1/3 in the end. That's all you get, simple multiplier. And this relates to what I was saying before. All of these graphs of the logarithm functions, they're simple stretches of each other. Remember, if you put a 1/3 in front, that's actually a vertical compression by a third, right? So the log 8x is basically a vertical compression by a third of the log 2x. Okay, so you always expect them to be related by these simple multipliers. You can turn a log into another log if you have the right multiplier in front of it, is the bottom line. Let's do that again. So let's take, maybe I'll do a different color. Let's take this thing, which is a log base 2 of x. We want to make it not a log base 2, we want it to be a log base 4. Okay, so how does this go again? You go like this. You say, I want a log base 4. So I'm going to set up a log base 4 on top of a log base 4. What goes into this log is the x. What goes into this log is the 2. So I got the x here, I got the 2 here. So again, we've got this situation where we can figure out what the log base 4 of 2 is. 4 to what power equals 2? It would actually be a square root, right? Think of roots as like powers that go the other way or something. So anyway, it's a square root, which means it's an exponent of 1/2. 4 to the 1/2 power is 2. So what we've got then is we've got the log base 4 of x being divided by 1/2. Now when you divide something by 1/2, that's the same thing as multiplying by 2. And so the log base 2 of x is actually the same thing as twice the log base 4 of x. It's exactly a factor of 2 to get the log 2 into a log 4. Exactly a factor of 2. Okay, we're moving now, folks? I got 2 more of these, and that's because these next 2 actually come up a lot in practical situations. Like here we have a natural log of x, and we want to convert it into a log base 10, a common log. Well, again, you're going to do a log over a log. That's what you want. You want a common log, so you can do a log over a log. On the top here, we're going to put the x. What are we going to put on the bottom? Well, we have to take this number, which by default is an e, recall. So it's the log base x on top, and the log base e, which you might leave it that way, but aren't you curious to get the decimal? I am. So I'm going to do the log base, and I have an e button on my calculator. So I've got the log base e. Turns out that's a nice number. That's called 0.43, roughly 0.4343. And so this is basically 1 being divided by 0.4343. So 1 divided by that is, if I make this into a multiplier, it's 2 maybe 303 or 3026, or depends how you want to round it. I'll say 2.3026 times the common log of x. The natural log of x is the same as 2.303 times the common log of x. Natural log and common log, they're multiples of each other, basically. One is 2.3 times the other. Let's go the other way. Maybe you'd want to try this yourself for a minute, right? Go the other way. Convert that common log, log base 10, into a natural log. You ready? So you're going to put a natural log on top of a natural log. And what goes in on top is the x, and what goes in the bottom is the base of the logarithm, which is 10. So this is a natural log of x over a natural log of 10. So what's the natural log of 10? Let's find out on the calculator. The natural log of 10 is, guess what? 2.3026. Oh, where have we seen that number before? Now this is like 1 divided by 2.3026. So if I do that, 1 divided by that answer, I'm getting, guess what? 0.43. Yeah, I'll just round it to 0.4343 times the natural log of x. I've seen this number a lot. It happens a lot. So a log base 10 of x, which is what this is the same as basically 43% of a natural log of x, 0.4343 times the natural log of x. Now, you're going to need this sometimes because when you go on the computer and you do a lot of Googling and stuff, you're going to see things written this way, and they're going to graph them and stuff. And it turns out they don't really mean log base 10 of x. They mean the natural log of x. That's what they mean. So if you want to take, if you wanted the natural log, if you wanted a common log, log base 10, and they're using as though it's a natural log and you need to convert back and forth, well, now you know how to convert back and forth. There's multipliers involved, depending which way you're going. So that's our second property. Change of base algorithm. Any logarithm is a simple multiplier times a different base logarithm. Pardon me. Those are the first 2 properties. We got 3 to go. Now these 3 are all kind of related. In fact, sometimes I call these the big 3. The big 3. So this is the first of the big 3. What's it saying here? It's saying the log of mn is the log of m plus the log of n. In other words, here, this is a product, right? When you multiply 2 things together. Now over here, of course, we have a sum when you add 2 things together. It's called the product to sum property because if you have the log of a product is the sum of, you can separate it out, separate the factors out, and add 2 different logs together. It's amazing how often we're going to use this property, so let's just get used to it. So again, whenever you have a product inside being plugged into a log, a bunch of stuff multiplied together being plugged into a log, you can split it up into different logs added together. Just split up the different factors. What's this one looking like? Well, we got three factors. It's not just an mn, it's a 6 times an x times a y. Well, it's a product. That's what matters. It's a product. So that means we can use this property, and we can split this up as the log of 6 and the log of x and the log of y, just like that. So it splits up very nicely. So 6 times x times y becomes log of 6 plus log of x plus log of y, like that. You might want to go the other way. Like here, we've got them all split up, and we want to put them back together. So this is a little different. This says the log of 5 plus the log of 6 plus the log of x. Well, that's kind of like, you've got this side, and you want to put them back together into a single logarithm. That's what it says. Write them as a single logarithm. So they were all split up and added. Well, now we're going to put them in the same log and just multiply them back together. In other words, it's the log of 30x. The log of 30x. So it's kind of a cool property, right? You get used to these things. So if you have a product, go ahead and split the product up. It's m times n, which means it's the log of m plus the log of n. Or you can go in the other direction. That's our first big property. First of the big three. Here's another of the big three. This is number 2 of the big three. Quotient to difference. So what's happening here? Well, if you compare this one to this one, notice that instead of plus, we got minus, but instead of times, we have divide. So it's a fraction. So if you have the log of m over n, then you're going to turn it into the log of m minus n. Okay, so that's kind of like the other side of the coin in some sense. So this one, this is kind of an m over n, where I've got this over this. Okay, so that means it's going to separate as log of, that's going to go there, and that's going to go there, right? So it's the log of 6 minus the log of xy. Let me write that out. I'm going to do this one kind of like this. There. So the log of the top minus the log of the bottom. That's what this property is saying. Now, actually, here, see, we can go a little further with that, right? Log of 6 minus, and remember, there's a property that says if you have an xy multiplying, you can split it up into adding. Now, to be careful about that, I suppose I don't need square brackets, but to be careful about that, you should split it up, and that should go inside parentheses like this. So the log of xy, maybe I'll do it this way, the log of xy like this is the same as the log of x plus the log of y like this. So if you want to subtract this thing, it's like subtracting this thing. You have to put it in parentheses to keep it as a single object. I'm subtracting that thing. And of course that's extremely important because a minus in front of parentheses tends to change things around, right? So what we've got here is we've got a log of 6 in front, distributing the minus. I got minus a log of x, and then I've got minus a log of y. That would be our final answer there. Splitting it up all the way. Log of 6 minus log of x minus log of y. I want to show you a shortcut to that, though. The 6 was on top, so that logarithm has a positive in front. This x was on the bottom, BOT for bottom, so it has a minus in front. The y was on the bottom, and that's why we have a minus in front. Okay? In other words, the x was down here, so it's minus log x. The y is down here, so it's minus log y. If you keep that in mind, it's going to be like really fast to do these things because you won't have to go through all of this parentheses action. I want to erase all that. It looks like a horrible mess. Okay, cool. Shortcut would be simply log of 6. Well, you can just see it. X is on the bottom, so minus log of x. Y is on the bottom, so minus log of y. Now, it's important that we have a 6 over xy. It's, there's no adding and stuff going on inside, nothing like that. It's just a straight product quotient type situation that enables me to do this. What's this one? Oh, this one's asking us to put it back together. Let's try to use this shortcut idea in reverse. If it's got a minus in front, it's because the x came from the denominator. If it's got a minus in front, it's because the y came from the denominator. If it's got a plus in front, it's because the 6 came from the numerator. This has got a plus in front. So the 5 comes from up top. This has got a plus in front. So the x comes from up top. This has got a minus in front. So the 7 comes from the bottom. This has got a minus in front. So the y comes from the bottom. Boom. These things are fun once you know the secrets, right? Whoops. Okay. I hope this thing's still working. Yep, good. So that's, I think, 4 properties. We got 1 to go. 1 to go. Is this the last page? Oh my gosh, this is so the last page. Okay, cool. One more property. This is the third of the big 3. So by the way, on the homework when it says make sure you use the big 3, it means you're using the 2 from the previous page plus this one. Okay, I'm calling this one the exponent property because what's going on here? Notice I've got x to the n power. If you've got x to the n power, this power sort of hops down front and multiplies. And of course you can go in the opposite direction. You could take the n and have it hop up as an exponent, right? So the log of x to the n is the same as n times the log of x. This, by the way, is a completely different thing. Okay, this is not what we're talking about. We're not talking about taking the entire log and raising it to the nth power. No, 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 no. We're talking about the thing that's plugged in here is x to the nth power. If you have an x to the n plugged in, this n can hop down front. Okay, so always be careful that what you're trying to do is an exact match to what the formula says. So 2 examples. One is break this up into a whole bunch of different logarithms, all added, subtracted, some difference of logarithms. Well, this is going to give us a chance to practice what we were saying before. If it comes from the top, it's going to have a plus in front. So I'm breaking this up as these 3 parts, right? So the 3 is from the top. It's got that logarithm has a plus in front. Square root of x is from the top. That has a plus in front. And then the y cubed is in the bottom, so that's going to have a minus in front, the log of y cubed. Okay, so that's what we were doing on the previous page, just splitting things up as a sum and difference. But we can take this a bit further now because of this new rule that we've got. First of all, this 3 is just going to come right down to the front, and this is going to be minus 3 times the log of y. Okay, that's using this property. And of course, that's just the log of 3. Not going to do anything with that. Plus, and then what's happening with this middle one, this middle term? Well, if you think of square root as meaning half power, exponent of 1/2, then it's like this is x to the 1/2. The 1/2 comes in front. And here's your answer. Pretty slick, right? Just bring that exponent down front. All right, one more. And this, of course, is going the other direction. We've got a whole bunch of logs all split up, and we want to put them all together. Put them all together. Well, in this case, the first thing we're going to want to do is these multipliers are going to have to hop up as exponents. We can't just leave them there. So that's the first thing I'm going to do. So this 2 is going to hop up, and I'm going to call that the log of x squared minus. And then this 3 is going to hop up, and I'm going to call it this the log of y cubed. And then this third is going to hop up, and I'm going to say plus the log of, and you could write 5 to the 1/3 if you want. You could write the cube root of 5, whichever you prefer. I'll just say 5 to the 1/3. Looks good to me. So anyway, we got all our, we don't have any coefficients in front anymore, so that's good. They all hopped up and became exponents. Now's the part where we can actually combine them together. This is going to become one big happy log. It's going to have some stuff on the top, some stuff on the bottom. How do I know that? Because we've got some stuff with pluses in front, and we've got some stuff with minuses in front. The stuff that has pluses in front, you know that came from the top. So this comes from the top. This has a plus in front, this 5 thing over here. So I'm going to put that up on top. I'll put the 5 in front of the x. It looks better. But this y cubed in the middle, it's got a minus in front. So the y cubed came from the bottom. And there you go. So these 3 logarithms can be combined together into a single logarithm just like that. And I'm at the end of the lecture already. I can hardly believe it. Okay, well, it takes a little, swimming in this stuff to get used to it, but we're going to need these properties a lot in the next lesson, so it's definitely worth the practice.